everybody, welcome to video 6 in the basic electrical series of videos. So this video, we're going to get straight into series circuits, their characteristics, and mathematically how to find your way around one of these. So first things first, back to kind of the last video, we talked about different types of circuits. We're going to utilize all the math from the last video, so if you haven't watched video 5 yet, you need to watch it in order to really understand this. I'm going to sort of breeze through some of the math because we already did it. So, all right. Very first thing to know, I've got some rules here. I hope it's not too small on the video. Working with what I got here. So I've laid out our rules. We got really 4 basic rules and characteristics to series circuits to know. Series circuit, by definition from the last video, was when we have multiple loads ran in a series or wired in a series, meaning we have, to our first rule or characteristic, we have one path for all loads or through all loads to go to our ground. So we've got one path for current to travel. It's got to go through all the loads in order to get back to ground. Here's why this one characteristic is flawed or has a problem for us anyways, is if I run into an issue, let's say where I have a break, let's say my light bulb goes out over here. Does that affect my first light bulb? It does. In a series circuit, if we have a break anywhere in the circuit, and this is any sort of the beginning of the circuit, if we've got a break up to our load, you're kind of screwed, nothing's going to work. But in a series circuit, if I've got a break in my first light bulb, in my second light bulb, in my ground, it doesn't matter, everything goes out. So the perfect example is like the old style Christmas lights were wired in series. So if any one of the light bulbs goes out, all of the entire strand goes out. Now they wire them a little bit differently where they have sort of these sections in series. So that's what a series circuit is. Now it's important to remember that. We'll come back to this later though. Current, the next rule is current is the same throughout the entire circuit. And this is similar to our simple circuit, right? So when we increase the resistance in the light bulb in the simple circuit, amperage went down, right? And if we decreased it, amperage went up. Well, the same thing happens here when first our resistances are going to determine the amperage in the circuit. I will say that once amperage is determined, it's the same from the beginning to the end. Remember, no matter what type of circuit it is, the amperage coming out of the battery is going to come back to your battery as well. So you guys can test that later on when you figure out how to do amperage testing. But there is whatever's coming out of the battery is coming back in. Now on a series circuit, it is the same in front of the light bulbs, after the light bulbs. It doesn't get split up. In a parallel circuit, amperage will actually come out one number. It'll sort of split up into different branches, but when it comes back to the battery, it sort of comes back in the same number. So hopefully that makes sense. But current is the same throughout the entire circuit. Please don't take that as current is the same in every circuit. That's not the case. If I've got 3 light bulbs versus 4 light bulbs versus 5 light bulbs, current is going to be different, right? Because resistance is going to be different, either higher or lower, whether we add light bulbs or take it away. So just keep that in mind. Our third rule is TCR, total circuit resistance, is the sum, if you don't remember that word, that is addition, right, of all resistance in the circuit. So if I have 2 light bulbs, in this case we've got one light bulb that has 1 ohm and another light bulb that has 1 ohm as well. So TCR, total circuit resistance, in my circuit is the sum of all resistors or resistance in the circuit. Purposeful resistance, well, and non-purposeful resistance in the circuit. So my total circuit resistance, which is going to determine my amperage, which is why that's important to us, my total circuit resistance, all I need to do to figure that out is to add these up. So let's do that real quick before we forget. TCR is the sum of resistance in the circuit, so let's add 1 plus 1. My TCR is 2 ohms. Easy peasy. Almost as easy as a simple circuit, except we had to do a little bit of adding. Obviously, numbers in the cars are not near as simple. They're going to be decimals, but I do want to make a disclaimer that it's not practical to try to get an amperage reading based off of what the specified resistance is, because things change. Resistance in circuits happen to change with heat and things like that, or temperature changes. So just keep that in mind. We're just talking theory right now. So in this circuit with two 1 ohm bulbs, we have 2 ohms in the circuit. That is our third rule. And then let's go back to current is the same throughout the entire circuit. We can actually find the math on that now that we have 2 measurements, right? So we want to know TCA. Let's do a quick handy dandy Ohm's Law pie chart. What are we looking for? We're looking for amperage. So let's go ahead and put our question mark there so we don't accidentally put something else that doesn't belong there in there. And let's fill in what we do know. We do know that our source voltage is 12 volts, and we do know that the total circuit resistance, now again, we're looking for the amperage for the entire circuit here, so we're going to go with the resistance for the entire circuit here, which is 2 ohms. We take 2 and put it into 12. That gives us a TCA of 6 amps. So we know the resistance, the amperage, and the voltage going through the circuit. Now, problem here is down here, we want to know VD1 and VD2. They're referring to voltage drop 1 and voltage drop 2, which brings us down here to our last rule of the circuit. Total voltage drop, and I have this very short here because I didn't have room to write it. I have total voltage drop equals source voltage. It must equal source voltage, right? I can't have any extra voltage coming back to my battery. So total voltage drop of VD1, of all my loads, right? So in this case, it's VD1 and VD2, is going to equal source voltage. So we can check our math on that. Now in a simple circuit, it's really easy because the load always uses up all of source voltage. So my VD is 12 volts for just the one load, and my source voltage is 12 volts, obviously. So let's figure out how it's split up. Now, some of you guys are probably saying, duh, you just split it half and half. In this case, yes. Let's do the math behind it because I'm going to give you a circuit in a moment here that is not the same number, and so you're going to have to figure it out. So we know here, I'm going to keep this, I'm going to erase our Ohm's Law pie chart here so we can figure out our VD1 and VD2. So when we're filling out our voltage drop pie charts, it's very important to put that question mark there, because if I'm going to do an Ohm's Law pie chart for VD1, I want to know how much voltage is being dropped here. We draw our Ohm's Law pie charts. If I don't put a question mark here, many of you are going to be very quick to be like, oh, 12 volts. We know it's 12 volts. So let's put our voltage there. Let's put our 1 ohm there, and let's put, let's put our 2 ohms there, and then let's go ahead and put our 6. Wait a minute, that's a complete pie chart. That doesn't make any sense. What was I looking for again? Exactly. That's why we have question marks. Not to mention I made another mistake here that is quite common. I don't want to know the voltage drop of the whole circuit. I want to know how much this one bulb is going to drop. And then I'm going to figure out how much my last bulb is going to drop. So be very careful. A, question mark for what we're looking for so we don't put things in the wrong place. And B, when I'm looking for voltage drop, what am I looking for the voltage drop of? I want to know the voltage drop of just this one bulb, not of the whole circuit. So for resistance, I need to put the resistance of just that one bulb. So for VD1, my resistance is simply 1 ohm. We are looking for voltage, but we do know our circuit amperage. Now remember, the amperage is the same throughout the entire circuit. So that one's pretty much a constant for VD1 and VD2. We know that our total circuit amperage was 6 amps. So we know with 6 amps going through 1 ohm that we used up VD1 used up 6 volts, which we predicted that, right? Now the math is exactly the same for VD2 because the resistance and the amperage is exactly the same. So it's nice and easy. 6 volts is how much our second one is dropping. Now if you want to double check your math, again, very basic stuff. If you want to double check your math, you remember total voltage drop, so VD1 and VD2, needs to equal source voltage. And if I add up 6 volts plus 6 volts, that equals my source voltage. So we did our math right. I'm going to give another example. A 2 ohm bulb and a 4 ohm bulb. And at home, I'd like you to pause the video right now. And I would like you at home on scratch paper to try to figure this one out on your own. So with a 2 ohm bulb and a 4 ohm bulb, what would your TCR be? What would your TCA be? What would voltage drop 1 be? And what would voltage drop 2 be? Now, don't cheat yourself here. I'm going to show you how to do it, obviously, but you're only going to remember it if you struggled a little bit yourself. So you should pause the video right now and try to figure it out yourself. All right, hopefully you did that. And now let's check your answers to see if it was correct. So, looking at our numbers here, TCR, we remember, is the sum of all resistance in the circuit. So all we had to do was add 2 plus 4, right? And that gives us a TCR of 6 ohms. Easy peasy, right? Hopefully that's what you got. TCA needs to be calculated by using handy-dandy Ohm's Law pie charts. What are we looking for? Amperage. So let's put our little question mark here. And what do we know? We've got 12 volts for the whole circuit. We're looking for amperage for the whole circuit. And how much is the resistance for the whole circuit? 6 ohms. 12, or how many times does 6 go into 12? That gives us a total circuit amperage of 2 amps. Boom. Hopefully you got those answers. If not and you're confused, send me a message or leave a comment and I will try to help fix. If you're like, where did you get this number, then let me know. Try to attach a time so I know what part of the video you're referring to as well. Now let's try to figure out voltage drop 1 and voltage drop 2. We're going to need that handy-dandy Ohm's Law pie chart again, aren't we? So let's go ahead and draw that. Again, what are we looking for? The voltage drop is what we're looking for. So we're looking for voltage. Remember, don't put source voltage there. And then again, we're not looking for both of the voltage drop of both of these. We're looking for just one at a time. So let's do VD1 first. The resistance of our first light bulb is 2 ohms. So we'll go ahead and put 2 ohms. We do know that amperage is the same throughout the entire circuit. 2 ohms for this one bulb and 2 amps for the entire circuit. 2, again, this vertical line is multiplication. So 2 times 2 is going to be 4. So the voltage drop of this first bulb is 4 volts. Notice it's not even anymore because the resistance is not the same. And I will show you exactly what this looks like on the electro trainer toward the end of this video, so you can see what those characteristics actually look like in person, well, not in person, but through video, physically. Let's try VD2. Now, since we know total voltage drop needs to equal source voltage, I could just take 12 minus 4 and we can figure that out. But let's do the proper math behind this here. Remember, you don't want to find shortcuts per se because it's not going to work all the time. If you find these like little patterns, they don't work 100% of the time. So let's go with the proper math here. We've got the same amount of amperage because it could have kept that, right? Because it's the same throughout the entire circuit. But the resistance is different for my second bulb here, and that is 4 ohms. So we'll go ahead and put that in there. And then we, again, know this is a multiplication line. So 4 times 2 is going to give us 6 volts, right? And obviously if I add 6 and 4, that will give me 12. So I know that my math was correct. So hopefully that's the answers that you guys got for that one. That is series circuits. If you guys want any more practice on that, just let me know. I will try to put out some numbers out there for you. But the same, if there was 3 or 4 bulbs, the same exact math would apply. It would just be multiple times, but the same pie charts would apply. So hopefully that makes sense. Again, if you guys have any questions, I remind you, please leave some in the comments. On Canvas, please put them in the discussion board so I can answer your question and hopefully help anybody else out as well. Let's go ahead and go to the electrical boards so I can show you exactly how those characteristics we just talked about in that math shows up in real life on the electro trainer. So I'm going to go ahead and flip the camera here. Okay, so what we're looking at here is a simple circuit like I showed you guys before. And it's important to start here if we're going to go into series and how the numbers that look in real life. So before I get to that, I want to just make sure that we see the brightness of the bulb. I will make sure and let you guys know when I'm using different bulbs right now. This one is what we call an 1187. It's just the number of bulb that we use for this electro trainer, but it does indicate a particular ohm reading. We can test that when we get into our ohm testing next week. Now, we've got, just to do a quick review as we're looking at our components, we've got our fuse, we have our toggle switch for our circuit control device, and we've got our power path, right, going into our load, then going to our ground path. Now, let's go ahead and take a look at what happens. We know what happens math-wise when we add another bulb in series. We know that we're adding more resistance to the circuit, which is going to drop our amperage, and we know that voltage is going to have to split up, but what does that really look like? So let's go ahead and turn this off here. We're going to go ahead and move this one a little closer to make room. Now, I think it's really important for us to make note here, if you guys were building circuits in class, you would need to make sure that you are making this clear power path. It's very easy to accidentally, plug wires and things where they don't belong, and we can easily create a short circuit. So anytime you're building any type of electrical circuit, even if it's on an electro trainer, if you don't want to pop any fuses, always double check your work before you turn on the circuit. That way we don't accidentally create a small fire or pop a fuse, right? So in order to make this from a simple circuit to a series circuit, I'm going to go ahead and disconnect my ground side here. And I could have put it in front, but I'm just going to go ahead and put the same 1187 bulb, so the same ohm rating, right here next to it. And these aren't always aligned. Okay, so now I need to finish the path. Remember, in a series circuit, I have to have one path into the first load, then out and into the second load, and then to ground. So we'll go ahead and connect our ground. But right now, since I have no wire connecting these, my light's not going to turn on. So we'll go ahead and add one more wire. I can use either color. It really doesn't matter. They are the same inside. The reason why I am color coding this for you guys is so you can realize I'm using the red wires to show you where voltage is still going to be, and then my black wires for where no voltage should be. Now, let's go ahead and see what happens. We know that we are looking at these two bulbs dimmer rather than the brighter one bulb because of a few reasons. And I know I'm kind of repeating myself here, but it's important to remember, since we added another load, we added in series, because remember, series circuit, we add another load, we increase resistance, and we remember from parallel circuits that wasn't the case. So we added a load in series, which increased our TCA, or I'm sorry, our TCR, which we know through Ohm's law decreases our TCA. So off the bat, we're dimmer partially because we've got we've got a couple things going on. One, we have less current flow, but two, and really important here, we started off with 12 volts, and first this was sort of the only child, right? It got all of the 12 volts, and now it has to split it. And we do know, because we did this up on the board, that since they're the same exact ohm value, they're going to use up the same amount of voltage. And I'll show you guys on the digital multimeters in next week's module what that's going to look like. But for now, we can physically see that they are dimmer for all those reasons. Now, did anything happen to our source voltage? No, but it did get split up as to where before it didn't necessarily have to. Now, I want to add in another bulb, which we know if we did, we'd probably see the bulbs get even dimmer, right? But what if that bulb had a different ohm reading? Let's check that out. So I'm going to turn off my circuit here. We'll go ahead and slide everybody over to make some space. And I'm going to add in another bulb. This bulb is called the 1152. So we'll go ahead and disconnect our ground here. I'm actually going to need one more red wire. Ran out, so we'll go ahead and move that underneath here. And we'll go ahead and bring this guy to part of our little family here. And now let's go ahead and connect our ground. Now we know they're going to be dimmer, but what do we expect to see? Do we expect to see a difference in brightness because of the different voltage level, or I'm sorry, the different ohm resistance levels? Do we expect them to take up different amounts of voltages based upon that? We should, because we did just learn that math. So which one will be brighter and which one will be dimmer? Whoa, that's crazy. So these two did get significantly dimmer. They're barely on. While this one over here is sort of stealing a lot of something, right? It's got to. Now, lots of students will think that, well, since it's brighter, it must have less resistance. Now, sometimes the logic behind that is, well, more resistance, less amperage, right? Yes, but this is a series circuit. So we need to remember that we have the same amount of amperage here as we do down here, as we do here. So it's definitely not an amperage difference because they're all getting the same amount of current flow. So what must be different? Well, we do know that ohms are different. They've got to be, right? Something has to be different. They're all getting the same, not necessarily the source voltage, but it's the choo-choo train of voltage going through our loads. Now, since this one is technically at the end of our circuit, wouldn't you think that these would get most of it and then this would get the residual? That's not how electricity works. Electricity will distribute, and depending on the type of circuit, in this case a series circuit, electricity or voltage will get distributed based upon the resistance, no matter where it's at in the circuit. So if I was to move this bulb over to the front here, then we would see the same exact results. This bulb would be the same brightness as it is right here, and these would remain the same brightness they are right now. So it doesn't have anything to do with where it's at in the circuit, but it has everything to do with the resistance value. Now in a series circuit, if we were to calculate, if you were to say which one's using up the most pressure, using up the most voltage, I mean, physically, we can see that this one is brighter while these ones are dimmer. So let's just throw in some arbitrary numbers. Let's just say what if this bulb was 2 ohms while each one of these were 1 ohms, kind of with what I'm saying right here. If it is going to have more resistance, math-wise, it should take up more voltage, right? So if I had 12 volts coming in, we know, if we are able to do a little mini pie chart here, we know we've got 12 volts coming in. Our TCR, if we were going to add them all up, is going to be 2, 3, 4, right? If you remember. So we have a total circuit resistance of 4 ohms. If we do some quick maths, we get 3 amps in our circuit. And again, these are arbitrary, but they're here to show us a little something here. And to prove my point, if we were to figure out how much voltage is getting used up, because we'd probably guess that this one's going to be the most voltage, the most pressure, it's brighter, right? We can do the math. So if we were to draw a little Ohm's Law pie chart in each one of these, or near each one of these, doing my best to try to draw with all these holes, we're looking again at voltage. What's that top gonna be? We do know on this bulb, my resistance is 1. We do know throughout the entire circuit that we have 3 amps. So this bulb right here, arbitrarily, would drop 3 volts. Well, we know the math is the same because the numbers are the same. Amperage is the same throughout, and it's the same resistance value, so we know this one would drop 3 volts as well. Well, if these drop 3 volts, 6 volts together, so far we've got 6 volts coming out of here. If you were going to guess, we're probably going to finish that up here, all those leftovers. So let's calculate that out. We've got 2 ohms, right? 3 amps again throughout the entire circuit. 3 times 2 does prove to us that this one does have more resistance, and therefore it's going to use up the most amount of voltage. So that is our series circuit in a nutshell. Now there's a couple of things that I want to talk about. Let me see if I can get rid of all this here so we're not distracted. I'll have to go back through with some cleaner. Let's test out a couple of things. Again, with a series circuit, I did mention that if any one of these light bulbs were to go out, it would cause the whole circuit to open up, no continuity, therefore I can't have any work being done. Well, let's test that theory. If I do my last light bulb or my first light bulb, is that going to make a difference? So let's try that out. If I do my first light bulb, they all go out. Okay, well, what about my second one? I mean, does it affect that one? Fancy that. They all go out. What about my last one? Fancy that. They all go out. So any break in our series circuit, no matter where, is going to cause a loss of continuity. Therefore, it will not function. Now, one more thing I'd like to discuss. What happens if I was, because we talked about short circuits a little bit, but in circuit protection, but what would happen if I was to maybe not bypass all of the loads, but what if I was to just bypass the second part? Like what if I had a piece of wire right here that ended up rubbing to chassis ground? Oh, craziness right there. Why did that happen? This happened because we gave electricity a choice. It is either going to travel to this point, and it's got a fork in the road, and it's either going to go to work and go home. It still has that option, but we gave it the option of taking a shortcut without having to do that extra work through the light bulb and get to go home. And electricity will always find the path of least resistance. And so if anything like that was supposed to happen or was to happen, that's the result we get. And now because it's bypassing that extra load, our total circuit resistance goes down. These two don't have to share the voltage with the last bulb anymore, and so these get 6 volts each again, and so we see those brighten up a bit. So just a couple of cool little things that we've got going on here. Also, I just want to mention my fuse. It's always very important to put as close to the power source as possible because if I have a short to ground, it puts everything else in danger if my fuse is later in the circuit, everything that's in front of it. So we always want this to be as close to our positive side as possible. But it's important to note my switch can be wherever I want. So I can take my switch and I can move everything over I can completely eliminate my switch here. Now, of course, I have no control. It's on all the time. But I can take my switch, I can put it in between light bulbs if I want to. I can put the switch at the end, at the beginning of the circuit. So I'll go ahead and disconnect this here. I'll put my switch at the end of the circuit, and we can see no matter what, I still have control, because all we're doing is having or creating a controlled open. No continuity, continuity. So that is how our series circuits work.